Okay, so last time we introduced finding the determinant of a matrix, a square matrix, and let's do an example from section 2.1 of Anton. So this says find or evaluate, that's what the Anton uses, so evaluate the determinant by inspection. What that means is just roughly by looking at this without doing too much computing, what is the value of the determinant of this matrix? Perhaps there should be like vertical lines here to indicate we're taking the determinant. And we saw that the idea or the definition of the determinant is to use an expansion along any row or any column of cofactors. And it turns out for this matrix, it's easiest to choose expansion by cofactors along maybe the first column or the last row, because there's a bunch of zeros in both of those. And you'll get the same answer regardless of which one you choose. And what I've done down here is choose column 1. So here's column 1, and look at the cofactor expansion. So remember, that's take the entries. So here's our first entry in column 1. Figure out what the cofactor, in other words, the determinant of this 3 by 3 matrix multiplied by a positive sign or a negative sign. And then we're going to take this 0 and multiply by the determinant of the 3 by 3 matrix that remains when we delete row 2, column 1. And it turns out that it doesn't matter what that cofactor is because we're multiplying by 0. And so 0 times anything is 0, so it's going to cancel out. Similarly, the 0 times the 3, 1 cofactor is going to be 0, so we actually don't have to do the hard computation of computing this cofactor, and similarly for the cofactor associated to the row 4, column 1 position. So all we have to do is figure out the cofactor associated to the 1, 1 position. That's again the determinant of the 3 by 3 matrix that remains when you delete row 1, column 1. And the cofactor bit is the minor multiplied by an appropriate sign. In this case, it's going to be positive 1. And okay, so then it remains we have to find the determinant of this matrix here. And for the similar reason, if we expand along cofactors along this column, we see that it's going to be 2 times the determinant of this 2 by 2 matrix consisting of 3, 3, 0, 4, because when we expand along this column, the 0s are not going to affect the answer, or they're going to turn into zeros. Okay, so we just have to multiply 2 by the cofactor of this matrix, and that's the determinant of the matrix times an appropriate sign. And then doing the arithmetic, we see that the determinant of this 2 by 2 matrix is just the diagonal 3 times 4 minus 0. Here's another 0. That doesn't affect the answer, and so it's just 2 times 3 times 4, and there was an original 1 up there. So what we see is it's actually just 1 times 2 times 3 times 4, in fact, just the product of the diagonal terms. And that's a general case of what's happening when you have a bunch of zeros, or what will happen when you have a bunch of zeros beneath the diagonal. The determinant is going to be the product of the diagonal terms. The values, the fact that these were 1s and 2s didn't appear didn't matter. It was really just the terms along the diagonal that contributed to this determinant. Yeah, that's what I've written up here, that this matrix is an example of what's called an upper triangular matrix. All the entries below the main diagonal are 0, and when you have such a matrix, which comes up quite a bit, in fact we'll see it later on today, is the determinant is simply the product of the entries in the main diagonal. Okay, let's move on to section 2.2, which is finding determinants via row reduction. And so we've seen in chapter 1 that row reduction can simplify a matrix to something manageable in some sense, or interesting. And so a natural question is, well, how does the elementary row operations change the determinant? And maybe we can use row reduction to find out the value of the determinant. And it turns out, yes, we can. So let's recall the elementary row operations. There were 3 of them. The first is multiplying a row by a non-zero constant. And the effect that that has on the determinant is that that multiplies the determinant by that constant. So here's an example. We start with this matrix. Its determinant is 4. Why? Because it's a 2 by 2 matrix. And so there, the determinant is just the product of the diagonals, which is 6, subtracted off the product of the off-diagonal elements, which is 2. And so we get 4. Now, if we multiply a row by 1/2, so I decided to multiply the first row by 1/2, so we get this matrix. And the determinant of this matrix is 2, and we see just by illustration that when we multiply it by this scalar 1/2, or sorry, I should say when we multiply by a particular row, not the entire matrix, but just a single row or single column, but in this case row, by a scalar or number, the determinant gets multiplied by that scalar. So this 4 got multiplied by a 1/2 to give a 2. And going back to the definition of determinant as expansion along cofactors or expansion via cofactors, you can see why this fact makes sense, that when you multiply a row, here I've written row, but the same result holds true for a column. When you multiply through by a constant, the determinant changes. It gets multiplied by that same constant. Okay, the next elementary row operation was swapping or interchanging 2 rows. And the effect that that has is it multiplies the determinant by -1. So here's an illustration. We started off with this matrix. Its determinant was 4. And then if we swap rows 1 and 2, we get this matrix. Its determinant is -4. So the determinant has been multiplied by a -1, and that's a phenomenon that's true in general. If you're wondering what's the explanation for that rule, well, it comes from the signs that are in the cofactors, that those signs, if you swap 2 rows, they pick up a negative sign. It's maybe a little bit more complicated than that, but we don't need to go into the proof right now. Let's just remember this fact. Finally, the third elementary row operation was replacing a row by adding to it a multiple of another row. And the good news here is that that does not change the determinant at all. So here we start off with a matrix that had determinant -4, and we replace row 2 by adding to it the double, or -2 times row 1. And we get this matrix here, and its determinant is -4 as well. This property in general is, a little bit harder to see. So once again, let me not go through the proof. Let's just accept this, and let's find out how we can use that to find the determinant of matrices using row reduction. So here's an example. We've got this matrix here, and the question is find the determinant using row reduction. So some operations involved in row reduction do change the determinant slightly, whereas this one here does not. Okay, so we're trying to find the determinant of A, and here's our notation. Vertical line just indicate determinant. Then and again, there's many different steps, as you know, in row reduction. Here, let's see, what have I done here? Well, because there's a minus sign, it means I must have swapped 2 rows, and that's indeed what I've done. I decided to swap the first and second row. Now you might ask, well, why did I do that? Let's scroll down a little bit and see the end result. Well, down here, let's see, down here, I've gotten my matrix in row echelon form, not reduced row echelon form, but just row echelon form. And I know from the example I did at the very beginning, maybe on the couple slides ago, is that when I have zeros below the main diagonal, the determinant of the resulting matrix is just 1. It's just a product, which in this case is a product of 1s. All right, so that's our goal, is we want to basically row reduce this matrix. So we need to bring a pivot 1 into this position here. So because I need some non-zero entry here, that's why I swapped row 1 and 2. Of course, I could have swapped row 1 and row 3. There's plenty of choices you can make. All right, now I'm going to divide out a 3 from this first row. And the resulting matrix I would get would then have this 3 becomes a 1, this minus 6 becomes a 2, and this 9 becomes a 3. And now you might say, well, okay, I divided out a 3, and then why am I multiplying by negative 3? Or, well, first of all, the negative comes from here. But why am I multiplying by this 3 instead of 1/3 dividing by 3? And the reason is, well, let's try to go backwards. If we start with this matrix, and what we're doing is multiplying this row by a 3. So according to our rule, the determinant of this matrix is 3 times the determinant of the matrix we started with. So that's why I'm multiplying by 3. So it's a little bit backwards. You have to, if you're dividing by 3, the determinant gets multiplied by that. By the scalar you're dividing by. Okay, and then again, just as a clarification, these vertical lines mean not matrix, but determinant. This is not scalar multiplication of a matrix. It's 3 is a number, and this vertical line is a number. It's the number that represents the determinant of the associated matrix. So that's why this 3 is not multiplying 0, 1, and 5. Okay, so then let's move on. So we've got our pivot 1 here. Then we're going to want to cancel this 2. Again, we're going back to chapter 1 in row reduction. And the good news is that this third step of replacing a row by adding to it a multiple of another row, that does not change the determinant. So this 2, I turned it into a 0 by replacing row 3 by row 3 plus negative 2 times row 1. So you can see the arithmetic here. I took row 1, multiplied through by negative 2, and then added to the original row 3. That's going to be my new row 3. And that does not change the determinant. So that's why I have the determinant here, and I didn't add anything new. I just copied over the negative 3. All right, so the next step is to turn this 10 into a 0, essentially, because then I'll be in row reduced form. And what I can do is replace row 3 by adding to it 10 times, negative 10 times row 2. And that's what I've done here. The new row 3 is row 3 plus negative 10 times row 2. Here's negative 10 times row 2. Do the arithmetic. I get negative 55. And okay, and so then what I'm going to do is factor out a 55 here. And so that's what comes here. And now I have a matrix that's in upper triangular form, namely 1s along the diagonals. And I know that its determinant is just a product, which in this case is 1. And so the determinant is minus 3 times negative 55, and that turns into 165. And so that's the answer. Okay, so let's do some exercises from the section. Here's problem number 21 on page 117. So we're given that we have this matrix here. Its determinant, that's what the vertical lines mean, is equal to negative 6. And the question then is find the determinant of this matrix. And you can see that it's some variant. They started off with this matrix and did a bunch of a few row reduction operations. Looks like multiplying the top row by negative 3. So we're going to have to use this fact, and namely this matrix, to somehow get this matrix, or maybe work backwards and start with this matrix, do a bunch of row reduction operations till we get this. Okay, so that's the solution. The solution starts here. We start with the matrix we're given, and we factor out a negative 3 from the top row. And the way that changes the determinant is like so. it factors out a -3 from the determinant. Okay, so now at least we've gotten the top two rows of our current matrix here consistent with the, or exactly identical to the matrix there. And then we have to figure out how to get this row into GHI. Well, we can replace this row by adding to it 4 times DEF, the second row. And when we do that, we get this matrix that we were originally given. And we're told that this matrix has determinant -6, and so there you have it, that the determinant is 18 of the matrix there. A general fact that's fairly easy to see from the definition of our determinant as expansion along any row or column is that if you have an n by n matrix, the matrix that's called A transpose, where you flip everything along the main diagonal, has the same determinant as the matrix you started with. It's easiest to illustrate with this by an example. So if you have a matrix A, like here's a 2 by 2 matrix, then the A transpose is you flip everything along the main diagonal. The main diagonal itself stays fixed. So this 2 goes over to a 1, and the 1 and 2 interchange basically. So, okay, and then we see in this particular example that the determinant is 6 in both cases. Okay, another fairly simple fact is that if a matrix has a row or column of zeros, then its determinant is 0. And the reason is, well, you just expand along cofactors along that row and you get 0. Secondly, if a matrix has 2 rows or columns, 2 rows or 2 columns that are the same, then its determinant is 0. And that's because when doing the row reduction, you'll subtract one row from the other, and that will give you a matrix with a row of zeros. Okay. If a matrix has a row that's a multiple of another row, then its determinant is also 0. And again, that's because you can, well, whatever in here is row reduced to get a row of zeros, or you can multiply by that scalar, that's this multiple, so that you get a matrix with 2 identical rows, and we're back in this situation here where the determinant is 0. And then all these statements above 1, 2, and 3 here, they hold that rows are replaced by columns. Okay, well, here's an example that says, let's see, look and see why the determinant of the following matrix is 0. So yeah, it takes a minute or so to, notice things, but based on, these 3 items, let's see, it says, is there a row of zeros? No, there's no row of zeros, no column of zeros, so that's not quite the reason why. Are there 2 rows that are are identical or the same? No 2 rows or no 2 columns are identical or the same. Does a matrix have a row that's a multiple of each other? Well, looking at this column here, everything here is a multiple of 2. So if we divide through by 2, we get 4, 1, 5, and -3, and that's exactly this column. So yeah, this determinant of this matrix is 0 because this column is double of this column here, and so by this property here with rows replaced by columns, the determinant is 0. And again, this property of why we can replace all the rows by columns in the above 3 statement is because a matrix and its transpose have the same determinant, essentially because of this theorem that you can use expansion along any row or any column to get the determinant. But that's a non-trivial result.